So in this section, we're going to look at some examples. Number one, let's say the lever shown let's say is uniform and has a mass, let's say, of 10 kilograms. Okay, so this is the lever. So let's say this is a wall. Okay, and we have this horizontal level over here, like this. And let's say this is the roof over here, and let's say it's supported by a string. Let's say that makes 37 degrees over here. Okay, and let's say the length of this one is 1 meter, and then we have a hanging weight over here. Let's say maybe 20 kilograms. Okay, and let's say this is about 0.25 meters. Okay, so the first question is calculate the tension in the string. A, calculate the tension in the string. Okay, so we have two unknown forces over here. We have this force over here, the tension in the string, let's call it T, but then we have another force over here, the force exerted by the wall. So we have two unknowns. So what we can do is, if you use the condition of rotational equilibrium and we put our point of rotation over here, then we don't have to worry about the force exerted by the wall. Okay, so we'll just have one unknown. Okay, when you do torque, it doesn't matter where you put your point of rotation because in equilibrium. So usually you put it at a point where there is an unknown force, so that you don't have to deal with that unknown force. That will help you to reduce the number of unknowns. You see, you've got force is the wall and the tension unknown in this problem, but if I put my point of rotation over here, then I don't have to worry about this force over here. I can just solve for the tension. All right, okay, now we have these two forces, but there is also the weight of the lever, which is 10 kilograms. Remember, if it's uniform, the weight can be assumed to act at the center of gravity, right? So this is 1 meter long. If it's uniform, the center of gravity is at the center. So we have the weight of the lever, 10 kilograms, acting over here and to the center, and this will be 0.5 meters. Okay, now the net torque should be 0 because it's in equilibrium, right? So we can say tau net equals 0. Okay, let's call this maybe weight 1 and this one weight 2. All right, so we have three forces over here. This the weight of the meter stick, the hanging weight over here, and then we got the tension over here. Okay, so we're going to say the torque d to weight 1 plus the torque d to weight 2 plus the torque d to the tension should equate to 0 because it's in equilibrium. Okay, so what is the torque d to weight 1? All right, so we're doing the torque about this rotation, right? So the distance, well, let's do them separately. Let's do this one first. Okay, so we have the distance is from here to here between the pivot and the point of application of force. Okay, well, let me say using the pivot of the wall. Okay, that is my pivot over here. All right, so this force over here, I mean this torque, you can say is the distance, the force, and then times the angle, okay, for this one. All right, so what is the distance? The distance 1 meters from here to here, okay, that's 1. The force is the tension, we don't know, T. Well, actually, I'm doing weight 1, so I'm sorry, let me do the other side. So first we're doing the torque d to weight 1, okay? So we have the absolute value of the torque d to weight 1 equals the weight 1 times the distance of weight 1, and then times the sine for the angle of weight 1. So what do we know? The weight for 1 is 20 times 9.8, approximately 20 times 10, okay? So weight 1 equals 20 times gravitational acceleration, which is approximately 10. So you've got 100 newtons for weight 1. How about the distance for weight 1? Is this distance, the distance in the pivot over here. This is my pivot over here. Okay, the distance between the pivot and this point over here. So this is 0.25, therefore this is 0.75. Okay, the distance from here to is 0.75. So you've got RW1 equals 0.75 meters. How about the angle? The angle is, so over here is 90 degree, all right? So we have theta 1 equals 90 degree. Therefore, the absolute value of the torque is 200 times the distance, which is 0.75 or 3/4 of a meter, and then sine of 90, which is 1. Okay, so you've got 50 times 3, that's 150. That is 150 Newton meters. Now we have to decide whether it's positive or negative. All right. So about this pivot, the tendency of this force over here is rotated in a clockwise direction. Therefore, it's negative. Therefore, it follows that the torque d to weight 1 is negative 150 Newton meters. All right. And then let's look at the torque d to weight 2. That is the weight of the lever. All right. And that's going to be, the force is going to be its weight. Okay, so W2 equals the weight of the lever times this distance, okay, and then times of this angle corresponding to the second weight, okay. So what's weight 2? The mass is 10 kilograms, okay. So that is m1 times gravitational acceleration. So the mass is 10, gravitational acceleration is approximately 10. So you've got 100 newtons for the weight. Okay. How about the distance for this one? It is the distance between this point and this point, which is 0.5, right? So you've got, this is 0.5. How about the angle? The angle is this angle over here, which is 90 degree. Okay. So you've got, this angle is 90 degree. So the absolute value of the torque is the weight 100 times the distance 0.5, and then the sine of 90. All right. So this one is 50. 100 times half. This is 1. This is half. So that's 50 Newton meters. All right. Now we have to figure out whether it's positive or negative. The tendency of this force about this pivot is rotated this way. That's clockwise, right? The force can be negative. So tau W2 equals negative 50 Newton meters. All right. And then finally, we're going to look at the work due to this tension over here. Okay. So let's look at the torque due to the tension. Let's look at this one. The work due to tension, its absolute value is the tension and then times the distance for the tension and the sine of the angle for the tension. So the tension we don't know, that we're looking for, and the distance for the tension is the distance between the point of application of force, which is this one over here, and the pivot. So the distance is 1 meters from here to here. All right, so the distance 1 meters. How about the angle? The angle is the angle between this line over here, okay, and this force over here, and these two angles are alternating angles, so they're equal. So our angle is 37 degrees. All right, so theta t equals 37 degrees. 37 degrees. All right, now we can say the absolute value of the torque due to the tension equals the tension, we don't know, the distance is 1, and the angle is 37 degrees. All right, so sine of 37 is 0.6, so you've got 0.6 times t. All right, now let's see, is it positive or negative? Okay, that is its tendency to produce clockwise or counterclockwise rotation. So you see this tension over here, which has this vertical component over here, its tendency is rotated counterclockwise, so it's positive. All right, so we can take it out of the absolute value sign and say just 0.6 t. All right, now we're going to go back to our equation. The torque due to weight 1 plus the torque due to weight 2 plus the torque retention. The torque retention equals 0 because in equilibrium. So let's plug in these numbers. So this one is negative 150, negative 150. The torque due to weight 2 is negative 50. This is negative 50. And this one is 0.6 times the tension equals 0. All right. So we have, this is 200. This negative value over here, so we've got 0.6 t equals 200, and so the tension is 2000 divided by 6. All right, and we can simplify this by 2. We get about 1000 divided by 3, which is about 333. It's about 333 newtons. So the tension in the string is about 333 newtons. Now we're going to say determine the force exerted by the wall. Okay, so now we're going to get this force over here. The wall is obviously exerting force on this lever, so we're going to get the force exerted by the wall on this lever. Okay, so let's call it force exerted by the wall, or the torque due to the wall. All right. All right. So let's call that force exerted by the wall, question mark. All right. Now we're going to use the condition of translational equilibrium. Okay. So that means the sum of the forces equals 0, using condition of translational equilibrium. Well, the sum of the forces equals 0, but we can use the components. So the x component of the force due to the weight plus the x component of the second weight plus tx, and now plus the force exerted by the wall x. This should equal to 0. Okay, so let's look at the components. Obviously these two weights are perpendicular, are vertical, so you don't have x components. Okay, so you don't have to worry about that. So let's just put 0 over here. So vertical forces didn't have components. How about Tx? Tx equals, you see this is the x component of the tension, Tx. That is the tension times the cosine of 37. You see this angle is 37 equal to this one. So that equals the tension times cosine of 37 degrees. All right. But we have already calculated the tension. The tension is about 333. So this is about 333 times cosine of 37, which is 0.8. Okay. So that is the x component. So that is we've got 24, 24, 26, 24, 26. So about 26.4 newtons, okay, times 0.8. All right, so you go back over here. We've got Tx plus Fwx equals 0. So this is about 266 plus this one, we don't know, equals 0. So the x component of the force exerted by the wall is negative 266 newtons. Okay, and for the y component, we use the y equation. That is W1y plus W2y plus Ty plus Fwy equals 0. Okay, now W1y, W2y, they just have vertical components. Okay, so this one has a weight of 100. It's going to be negative because it's down, so this will be negative 100, and this one is mass times gravity, 20 times 100, and it's going to be negative 200 because it's down and doesn't have x components. Okay, and how about Ty? Ty, this one over here, is the tension times the sine of 37. Okay, that is, the tension is about 333 and sine of 37 is about 0.6. Okay, and that is, we've got 18, 19, 19, about 200 newtons. Okay, so let's plug the numbers. We've got negative from these two, we got negative 300 plus 200 newtons plus the y component of the force is the wall equals 0. So it follows that the y component of the force is the wall is about 100 newtons. Okay, so we have both the x component and the y component, and if you want the magnitude, it would be Pythagorean theorem. That is the x component 206 squared plus the y component, which is about 100 squared. Okay, so that would be the magnitude. Of course, the direction would be tan inverse of the y. The y is 100. The one is 100, and the x is negative 266. But remember, if the x component is negative, you gotta add 180 degree. Okay, so these are the magnitude and the direction of the force. Right. Now we're going to look at another example. In this case, we're going to look at a ladder resting on a wall. Suppose, let's say this is a wall over here. This is a wall, and then let's say we got the ladder over here leaning on the wall. Okay, let's say this angle over here is maybe 53 degrees. Okay, all right, now suppose the length of this one is let's say maybe 4 meters. Okay, let's say the length of this one is 4 meters. Okay, and let's say we have a man standing over here, and let's say this distance over here is 1 meters. Okay, so the question is a ladder of mass, let's say 5 kilograms, is leaning on a frictionless wall. Okay, this ladder is uniform. Okay, so let me put uniform over here. All right, a man of mass, let's say 80 kilograms, is standing at a distance of 1 meters from the ground along the ladder. Okay, so this man over here has a mass of 80 kilograms. Okay, all right, and the ladder has a mass 5 kilograms and is uniform. All right, so the question is, calculate the force exerted by the wall. We're going to say calculate the force exerted by the wall. Okay, so looking at the force exerted by the wall, now let's see the force exerted by the wall. This is a surface force. It has two components. One is the force of friction, which is parallel to the surface, and one is the normal force, which is perpendicular to the surface. But we're told it's frictionless wall, so we don't have the force of friction. We have only normal force. Okay, so the direction of this force must be perpendicular to the surface. Let's call it F wall because there is no friction. There is another force over here, the force due to the ground. Okay, so in order not to worry about this force over here, we're going to put our pivot over here. If you put our pivot over here, the torque due to the force exerted by the ground will be 0, so we don't have to worry about it. Okay, and then we have the weight of the ladder. It's uniform, it acts at the center. Okay, so the ladder is 4 meters long, so this would be 2 meters. Okay, and the weight would be acting over here, and its mass is 5 kilograms. 5 kilograms. This man over here has a mass of 80 kilograms. Okay, so let's give this names. So this obviously would be force due to wall, exerted by wall. Okay, let's call this maybe let's call W of man, weight of standing man, okay, and then we have the weight of the lever. Let's call WL, weight of the lever. Okay, so if we take torque about this point, all right, we have the following three forces acting: the weight of the man, the weight of the lever, and the force due to the wall. Okay, so the torque is these forces should be, if you add up the torques, these three forces, it should be 0 because the ladder is in equilibrium. Okay, so the torque due to the force due to wall plus the torque due to the weight of the man plus the torque due to the weight of the lever should add up to 0. Okay, so let's look at this three torques separately. First, let's look the torque is the force of the wall. No, we don't know this what we're looking for. So first let's do the absolute value. This equals the force due to the wall, the distance of this force, Fw, and then the sine of this force over here. Okay, the force is the wall, we don't know, question mark. How about the distance? The distance, this is the distance between our pivot and this point over here, which is 4 meters. Okay, we're told this is 4 meters over here. So that is 4 meters. How about the angle? Theta Fw, the angle is this force. Okay, this is the angle between this line over here and this force over here. Okay, so you see the angle between this force and the position vector of this point with respect to pivot is this angle over here. But you see these two angles are alternate interior angles. Alright, so they are equal. So this angle over here is also 53 degrees. Alright, so this equals 53 degrees. Alright, so let's calculate the absolute value of the torque due to the force due to the wall is, we don't know the force due to the wall, the distance is 4, and then you've got the sine of 53 degrees. The sine of 53 is 0.8, so you've got Fw times 4 times 0.8, so we get 3.2 times the force due to the wall. Now let's see whether it is positive or negative. So what's the tendency of this force over here? Its tendency is to rotate this way, to rotate like this, which is clockwise. Okay, so this should be negative. So this is negative 3.2 times the unknown force due to the wall. Okay, next let's do the torque due to the weight of the man. All right, just torque. Okay, this torque, this absolute value, the weight of the man, equals the weight of the man times the distance of the weight of the man times the sine of the angle for the weight of the man. Okay, what's the weight of the man? Well, we're told his mass is 80 kilograms, right? He mass 80 kilograms, so his weight is 80 times gravity, which is about 10. So this equals, well, the mass of the man times gravitational acceleration is 80, and gravitational acceleration about 10, that is 800 newtons. Okay, how about the angle? Well, first let's look at the distance. Okay, that is the distance between the point of application of the force, which is right over here, and the pivot over here, and that distance we're told is 1 meters. You see it's 1 meters over here, so our distance is 1 meters. How about the angle? Okay, the angle is the angle between this position vector over here, okay, and this force over here. So the angle we're looking at is this angle over here. Okay, so you got a right triangle over here. If this is 53, this angle should be 37. Okay, we're looking at this angle over here, so the angle is 37 degrees. So this equals 37 degrees. All right, so now let's calculate it. So the torque is weight of the man, is the weight of the man, about 800. Its distance is 1, and the angle is 37 degrees. Sine of 37 is 0.6, so this gives us 480 newtons. All right, now let's see whether it's positive or negative. The tendency of this torque, this is a pivot, so the tendency of this torque is to rotate it in a counterclockwise direction. Okay, this force over here, so it's going to be positive. So the torque, which is the weight of the man, is 480 Newton meters, because its tendency is produce counterclockwise rotation. And then let's look at the torque. This is the weight of the lever. Okay, so that's going to be absolute value of the weight is the lever equals the weight of the lever, the distance of the weight of the lever, and then the sine of the angle of the weight of the lever. Okay, so the weight of the lever is the mass of the lever times gravitational acceleration, and that is 5 kilograms. Okay, the weight of the lever is 5 kilograms times 10, gravity approximately 10, that is 50 newtons. How about the distance? Well, it's uniform, so it's halfway. Okay, so from here to here is 2 meters. The whole thing is 4 meters. So from here to is 5 meters. It's the distance between the pivot and the point of application of the weight of the lever is at the center because it's uniform and the weight acts at the center of gravity. Okay, so that one, the distance of WL is going to be 2 meters. How about the angle? Okay, we're looking, this is the angle we're looking at. This angle over here, you see this is our position vector, this is the force, and this angle is 53, this must be 37 degrees. So the angle is 37 degrees. This equals 37 degrees. So let's calculate the absolute value. That is 50 times the distance 2 times the sine of 37 degree. Okay, so this is 100, this is 0.6, so you get 60 newtons. The force is 60 newtons. All right, now let's see whether it's positive or negative. Okay, that is whether its tendency is clockwise or counterclockwise. So the tendency of this torque over here about this point is clockwise. Its tendency to rotate this way, counterclockwise, so it should be positive. All right, so we have the torque is actually positive 60 Newton meters. All right, now we have all the torques, we can add them up together. Okay, so you've got the torque due to the force of the wall plus the torque due to the weight of the man plus the torque is the weight of the lever should equate to 0. Okay, so we have all these three values. The torque, this one is negative 3.2 times the force, the unknown force. This is negative 3.2 times the force due to the wall, and the weight due to the weight of the man is 480. This one is 480, and the force due to the weight of the lever, the torque, is 60. So we've got plus 60 equals 0. Okay, so we have 3.2 times the weight force due to the wall equals, that is 180 plus 60 is 540. Okay, so the force due to the wall is 540 over 3.2, or divided by 32. Okay, so I guess can we simplify this? By 4 would be 8, by 4 would be 1 plus 14, 120. Okay, by 4 this is 8, this would be 1 times 14, 3 times 20, 5 times, okay. And still it can be divided by 2. So we're going to 350 over 8, and then if you divide by 2, we have 6 times 7 times, no, I can divide by 2. 6 times, we got 1, 7 times 1, 5, okay, 375 over 4. Okay, so this is the force due to the wall, Newton. Okay, now B, we're going to say calculate the force exerted by the ground. Okay, so now we want to calculate this force over here. There is a force over here. Okay, the force is the ground. All right, it could be something like this. Okay, so we want to calculate the force due to the ground. Let's call it Fg, the force due to the ground. Okay, so I'm going to use Fg, force due to the ground, force exerted by the ground. Okay, so I'm going to use conditions of translational equilibrium. So the first one would be the x component of the force due to the wall plus the x component of the weight of the man plus the weight component of the weight of the lever, and then this unknown force Fgx equals 0. Now these two are vertical forces, so they don't have x components. Okay, so it's just the x component of the force due to the wall plus the force exerted, the x component of the force exerted by the ground equals 0. But what is the force exerted by the wall? We just calculated, it's this one over here, and it is to the right and it's horizontal. Okay, so the force, the x component of the force of the wall is itself and positive because to the right, because horizontal. So this is 675 over 4 plus the force exerted by the ground equals 0. So the force exerted by the x component of the force is the ground is negative of the force exerted by the wall, which is negative 675 over 4 newtons, which means it's to the left. You see, the only horizontal force in this problem is this one over here, and keeping the equilibrium, this one has to exert the same amount in this direction. Okay, that's why this is the negative of this. Actually, this doesn't reflect that, but all right. And then we're going to do the same thing for the y component. So the y component of the force due to the wall plus the y component of the weight of the man plus the weight component of the weight of the lever, and then the unknown force, the force is the ground, is y component equals 0. Now this force over here, the force is the wall, is horizontal, therefore its y component is 0. And these are vertical forces, so the vertical component is itself but negative because it's downward. All right, and this forces over here, the weights for the man is 800 newtons, and for the lever it is 50 newtons, so they're 850. We have already calculated them. The man is going to be negative 800, the lever is going to be negative 50. Okay, so that follows that the y component of the force exerted by the ground is simply 850 newtons. Okay, if you want the magnitude of the force, then it would be the square root of this over 4 squared plus 850 squared, and of course the direction would be tan inverse of the y component at 150 the x component is negative 665 over 4, and if that is negative, we have to add 180 degrees. Okay, so this will be the direction. And now let's consider another example. Let's go to the other page. This third example. Now suppose we have the following situation. Suppose we have let's say a crane centered or pivoted on the ground like this. So this is a crane. Okay, let's say there is a wall over here, and let's say is first let me give, let's say this is 10 meters, and then we've got a string supporting it over here, pulling it this way. Okay, and let's say this distance over here is 2 meters, and then let's say there is a mass of 1000 kilograms hanging from here. Okay, so this is a crane over here, it's pivoted over here. So the question is to calculate the tension in the string over here, which is supporting it. So the string is pivoted over here. All right, so the question is, the crane shown is uniform, let's say, and has a mass, let's say, of, I don't know, maybe 20 kilograms. All right, okay, is uniform, has a mass of 20 kilograms. So A, the question is, calculate the tension in the string. The tension in the string. Okay, now we have two unknown forces. We have a force over here exerted by the ground on this crane over here, and you've got this tension over here. Okay, we need this angle over here. Let's say this angle is maybe 37 degrees. All right, okay, you've got this hanging weight over here. So calculate the tension in the string. So we're going to use T for the tension in the string, and then you've got the weight of this hanging object. Let's call WH, weight of hanging object, weight of hanging object. And then of course we have the weight of the lever. It's uniform, so it's going to act at the center. This is the weight of the lever, and of course it's uniform, so it's going to be halfway. That's going to be 5 meters. Okay, all right, so let's say this is weight of the lever, weight of the lever. Okay, so now we have two unknowns, the tension T and the force exerted by the wall over here. Okay, now if you put our pivot over here, we don't have to worry about the force, the force exerted by the ground, because its torque will be 0. So I'm going to put my pivot over here. Okay, this is my pivot to solve the problem. It doesn't matter where you put your pivot, but it makes the problem a lot easier to put the pivot over here. So there is an unknown force over here, and if you put the pivot over here, you don't have to worry about that. All right, so we have three forces: the tension, this weight of the lever, and the weight of this hanging object over here. So we can say that the torque due to the weight of the hanging object plus the torque due to the weight of the lever, and plus the torque due to the tension equals 0. Okay, so this is the equation we're going to use to solve the problem. Now let's start with the torque due to weight of the hanging object. Okay, its absolute value, weight of the hanging object is going to be the weight times its distance times the sine of the angle weight is the hanging object. Okay, so what's the weight of the hanging object is 1000 times gravity. So weight of the hanging object equals the mass of the hanging object times gravitational acceleration, which is approximately 10. Okay, so we have, this is about 10,000 newtons. 10,000 newtons. How about its distance? Its distance is 10 meters. It's a pivot, is a point of application force, so that is 10 meters. So we have the distance for the hanging weight is 10 meters. How about the angle? This is the angle looking at. This is the position vector. This is the force, this is the angle looking at. If this angle is 7, this angle should be 53. Okay. So the angle for the hanging weight is 53 degrees. Okay. So you can calculate now the, let's calculate its absolute value. It is the weight of the hanging object, which is 10,000, times its distance, 10 meters, and then sine of 53 degrees, which is 0.8. So this is 100,000 times 0.8, that's going to be 80,000. Okay, 80,000 Newton meters. Okay, and now let's see whether it's positive or negative. You see about this pivot, the tendency of this torque is rotated in a clockwise direction. Okay, so it's going to be negative. So we take this out, absolute value, the weight of the hanging object, that is negative 80,000 Newton meters. Okay, and then we're going to do the torque. This is the weight of the lever. Okay, let's do that. So the absolute value of the weight of the lever is the weight of the lever times the distance and then times its angle. Okay, so the weight of the lever is, its mass is 20 kilograms, and then gravitational acceleration is about 10, so it's going to be 200 newtons. Okay, how about its distance? Its distance, this is the center, so it's going to be 5 meters. All right, so its distance is 5 meters. It's 5 meters. How about its angle? Its angle, you see this is the position vector, this is the force, so we're talking about this angle. This angle is 37, so this must be 53 degrees. All right, so that is 53 degrees. So let's calculate the torque. This is the weight of the lever, equals 200 times the distance 5 times the sine of 53 degrees. Okay, this is 1000 times 0.8 is 800. Okay, now let's take it out of absolute value. Okay, let's see whether its tendency is clockwise or counterclockwise. About this pivot, this has this weight over here has a tendency of causing clockwise rotation, so it's going to be negative. All right, so that equals negative 800 newtons. Okay, all right, and then we're going to look at the torque due to the tension. The torque due to the tension. Okay, its absolute value is going to be the tension, and then this distance, and then sine of its angle over here. Okay, the tension, we don't know, that's what we're looking for. And the distance, you see, this is 10 meters from here to here, and this one is 2, so this distance over here is 8. All right, so its distance is 8 meters. All right, how about the angle? The angle, this is the angle between this position vector and this tension over here. So you see these two angles over here are alternate angles, are equal. So this is 37, this angle is also 37. All right, So we have theta t equals 37 degrees, okay? So the absolute value of the torque is the tension, is the unknown tension, times the distance 8, and then times sine of 37. Sine of 37 is 0.6, so it's going to be 4.8 t, okay? Now we're going to add all the torques and equate them to 0. So the torque is the tension, plus the torque in the weight of the man, plus the torque is the weight of the lever, equals 0, okay? So the torque due to the tension is 4.8 t. Well, by the way, that has a counterclockwise tendency, so this is positive, okay? It has a counterclockwise tendency. And then the torque is the weight of the man, of the, weight, hanging object, I'm sorry, is negative 80,000. This is hanging object. This is minus 80,000. And then the weight, the torque due to the weight of the lever is minus 800, okay, equals 0. So we've got 4.8 t equals 80,800, and then the tension is 80,800 divided by 48, okay, or 80,800 divided by 48, okay. Of course that could be simplified. Let's see, by 4 is 20. Let's do by 4. By 4 this would be 12. By 4 this would be 20. By 4 this would be 20, and then 0. So you've got 20, 20, 0 divided by 12. Again, you can divide by 2, so it's going to be 10, 10, 0 over 6. Okay, so this is the tension in the string. Okay. All right. Now let's say calculate number 2. Maybe it's B. Calculate the force exerted by the ground. The force exerted by the ground. Okay, so we're going to use the condition of translational equilibrium. So the x component of the tension plus the x component of the hanging weight plus the weight, the x component of the weight due to the weight of the lever, and then this is the hanging object, and then the force is the ground, x equals 0. Okay, we're going to use FG for force exerted by ground. Okay, so Tx is a horizontal force to the left. Okay, so it's just negative of this number over here, negative 10100 over 6. You see these two do not have x components. Okay, so plus 0 plus the x component equals 0. So the x component of this one is simply 10100 over 6. How about the y components? You've got ty plus why plus wly plus fgy equals 0. Okay, this is a horizontal force. It doesn't have any component. The hanging object is a vertical force, so the vertical component is going to be itself but negative, and that is 10,000. Okay, so this is negative 10,000, and the weight of the hanging object, of the lever, is 200 newtons. Okay, that's downward is going to be 200. Okay, plus FGY equals 0. So this component over here is simply 10,200 newtons. Okay, so these are the x and the y components.